All right, the final of the whatever these are videos. Take a seat, kids. Apparently, I need some updates, but I'm not going to deal with that right now. Is that really never going to go away? Yeah. Go. All right. So I had to sub a little for sister this week, and apparently they call the endpoint the equivalence point in honors. So I will never ask you such a word, but I'm going to put it in my notes now. Will I? I don't know. So acid-base titration, we've done this, and it's a fun lab. And you had a online virtual lab that you could have done and a real lab that you could have done. And I like both of them. So the point here was that you are adding to a bunch of acid. Let's try that again. So you had in your flask a bunch of acid, so a bunch of H plus, and then you would try to neutralize some of that H plus by having on your thing a purette full of OH minus, right? And this had OH minus. And every time an OH minus would come down, it would take out one of the H pluses and make water. But the solution would still stay red because you still had H pluses, right? You still have all these H pluses down here. Not including that one, of course, because that's now water. So the pH still stays acidic. And then after you add enough OHs, it will become neutral at 7. And then after that, it'll go basic. So I should have moved this up a little, I guess. But you start here-ish. And then to get here by adding base, you have to go through here. And the idea was to draw a line on those guys. The idea was to stop here, because at that point you are at the equivalence point, the point where, love this computer, the point where, right, go away, the moles of hydroxide equaled the moles of H plus in the solution. And that meant only water existed, so the pH was 7. And we use an indicator to do that, and I showed you a pH meter that we could have done, or we used the universal base, or the universal indicator that changes different colors, and we also used the phenolphthalein, which only changes to one color when base is there. So the point of all this is, since we're looking at moles and moles being equal to, then if we had moles per liter times liters, that would be moles, and moles per liter times liters, that would be moles, and the moles of base and the moles of acid would be equal when the OH is equal to the H plus, right? So that works. Now it turns out this equation also works if you put milliliters here and milliliters here, because that's the same as dividing both sides of the equation by 1,000 as liters, and that's fine, or times 1,000, I guess, times 1,000, both sides, right? Multiplying liters by 1,000 would be giving you milliliters, and if you do it to both sides of the equal sign, then it's the same as if you didn't do it at all, kinda. All right, so this works for milliliters and it works for liters. Just make sure the same thing is on both sides. So here's an equation or a question, and remember the key word here is this letter, this word of. Of will connect two things, and those two things are either the base or the acid. So in this case, those are the base, because that's KOH. So you have your molarity of the base is 0.50. Whoa. I literally just leaned on the side of my thing. Anyway, 0.500 molar is the molarity of the base, and the volume of the base is 30 mils, and that's fine as long as the other one's in mils. Look at there, the other one's in mils. So that would be your VA, would equal 10 milliliters. And unknown, here's the word of, connecting it to the word unknown. So 10 is being connected to unknown. So the MA is your X. And then you just plug all that in, so that X times 10 equals 0.5 times 30. And what you get there is 1.5. X equals 1.5. And the units of that are molarity. All right. So that is a way to determine the concentration of an unknown thing, like we did in the lab. And here, Jimmy Jr. used too much base and he over titrated. So what happened to Jimmy Jr. was he was trying to stop here, and instead he went all the way over here. And so what the professor or the teacher said is like, hey, you know what? We can make it go back to acid by adding a little bit of acid. So that's what happens in this situation. So Jimmy Jr. adds too much and the teacher gives him 2 more mils. So he started with 10, he went too far, so they now have a total of 12. So the volume of the acid is now going to be 12 mils. And mils is fine as long as my other thing's in mils, which it is. The molarity of the acid is still unknown, so that's the X. And you see here the word of is connecting these two words, so that would be the molarity of the base is 0.1 molar, and the volume of the base is 16.7 mils. And then you just plug all that in and solve for X. So X times 12 is equal to 0.1 times 16.7. And I forget what that is when you do it all out. I guess I could do that. We'll discard all that. So it's 12x equals 0.1 times, here we go, 16.7 times 0.1 equals that, and then we're going to divide that by 12. So the answer is 0.139. So remember that when I get this up and running again. Of course, that's not what I wanted. 0.139. So we had 16.7 times 0.1 equaled to 12x, and then x equals 0.139. And that is the molarity, because the 12 mils came from 10 plus 2 milliliters was your VA, and your MA was a question mark. All right, apparently the screen wants to move on. So as a picture, and I did this with the pH probe, this is what it looks like as a picture when you do this titration. So again, you have in here a whole bunch of acid, and when you add some base, right? So here's our base stuff coming down, and an OH minus pulls out one of those. When the first one leaves as water, that's nice, but we're still in acid. We're still here in the acid region, right? We're down, oops, there we go. We're here in the acid region, right? pH of 1 to 2. So as you add more base and you knock out more and more of these things, as you add more base and you knock out more and more of these things, right? You get more and more water. And all of a sudden, when you knock out the last one, all you have is water. So you get to a pH 7 for a very brief second, right? You get right here, which is pH 7, because everything has turned into water. So we got water and we got water and we got water, and it's nice pH 7 water. Then the problem is you add another drop because you go too far or whatever, or if you were to add another drop, so then you add one more drop of OH minus, and it goes in there, and there's no more H plus for it to react with. Boy, is this a busy picture. But here it is, my last drop of OH minus, and there's no more H plus. This one's gone, this one's gone, this one's gone, this one's gone. So there's nothing left. So the OH minus is now going to dictate the pH, and the pH shoots up very quickly to the 12-14 region, because now you've basically neutralized all your acid and you're up to a base. All right. So then I asked you, well, then what's going on here? You have 2 equivalence points. And what we were hoping to see is that something happened where you have acid, right? So you have a low pH, so a pH of 1 to 2. And then you get your equivalence point at 7, like we expected. And then for some reason, it happens again. It happens a second time. So what's this? What is this? Is the question. Down here, it's definitely an acid. And then up here, it's definitely a base, right? Up here, it's definitely a base. And the question is, and here, it's definitely water. Oops, this is definitely water, right? pH 7. So what happened there? And what we determined is if you have one of these funky acids, like H2, H2SO4, there's 2 H's that can come off. So when that first H comes off, I'm running out of room to write all this. So that first H comes off, H2SO4 goes to H plus HSO4 minus, and then HSO4 minus goes to H plus SO4, 2 minus H plus. Eesh. Bear with me, kids. All right. So what happened in step A is happening here. You're pulling off this H plus with some base. So some base is here, right? Because we're adding base. That's what this is. We're adding more and more base. So the first base is pulling that off, turning that to water. And then you're left with this thing. And what that thing is a very weak acid or a slightly basic salt. Not really a salt, I guess. And that's what happens here. What's happening here is you have it's HSO4 minus 1, this stuff here. And because of that, adding more hydroxide, adding more OH can rip off that last proton and become SO4 minus 2, which is even more basic. And that is what's happening here. So this point B is this thing, because you're now trying to pull an H plus off of an overall negative species. And as you must have learned by now, that opposites attract. So if I'm trying to pull an H plus off of a thing that's overall negative, that thing, right? This is an H plus connected to that piece. Anyway, so trying to pull that away when the overall thing is minus 1 is difficult to do versus here where it's neutral. It's a little easier to pull one H plus off. So in part A, you can pull off that first one kind of easy with the OH, but the second one, it takes a lot more OH to convince the HSO4 to rip that off. So what we call this is a diprotic right here, diprotic acid, right? It has 2 H's on it. And that's actually a weak diprotic. What I've used is a strong diprotic, but that was just for simplicity. Here we go. So Bronsted, the last thing, Bronsted said a acid is a proton donor and a base is a proton acceptor. And the proton donor comes from anything that can basically give up an H plus, right? And that's sort of basically what Arrhenius said, that it produces H plus in water. Well, the acid is the thing that gives you the H plus. And then the base, this is a nicer thing because while it's true, OH minus is a base because it can accept that H plus and make water. But what about ammonia, right? This is a base. And the reason it's a base is because this H plus can kind of just hover here with this lone pair and kind of loiter around that lone pair and pretend it's his, even though it's nitrogen's. And it gives nitrogen that overall plus charge. But nitrogen is a base in that case because it's basically sucking up an acid, right? It's taking that acid and occupying it so it can't do the destruction it usually wants to do. So because of that, and because of what we talked about, things being in equilibrium and going backwards and forward, then in the case of where this is a base and this is an acid, right? And this is an acid because it's giving up the H plus. Then on the other side, we have what is I guess right here, a conjugate acid. Because now when it goes in the reverse direction, when it goes this way, this is giving up the H plus, right? This H plus is coming off of here. And the conjugate base, this is the conjugate base. The conjugate base is the OH minus because going that way, it's picking up the H plus, which is what a base does. This is the proton acceptor going backwards. This is the proton donor going backwards, right? This stuff is the proton donor going backwards. In the forward direction, this is the acid because it's giving the H, and this is the base because it's accepting the H. So we played a little game in class, depending on which class you're on, where I had H plus cards, right? And whoever had the H plus card, right? In this case, that would be water. So if water has the H plus card, I have the H plus, right? Here's the H that it has. And it gave that H plus to this base, and now it made that an acid, right? It added that H plus to that base. So now what's left in water is a base. What's left with water is a base because it doesn't have that H plus anymore. And what's left with the ammonia is an acid because it picked up that H plus. And then going in the opposite direction, if you recall in the game we played, the people who got the H plus were now the ones who could stand up. So they are now the acid because they have the H plus and they could go to water or some other thing and give it back, right? So you need to identify in this the acid and base. And it's sort of like a tag, you're it, right? Acid gave the H plus to this base, and now it's it. It is quote unquote it, right? All right. Right. So that's like, that's, that is it, right? That's Pennywise. All right. So, and then going the other way, it gives the H plus back to OH minus, and now water is it, as it were. It's the acid. All right. So then the last thing I kind of showed for people is what this idea of Lewis acid, and this is a great idea. Lewis acid is like, why just say H plus has to be the loiterer? Here's BF3, and if you recall, BF3 only makes 3 bonds. And even though there's such a thing as an octet rule, why didn't it make a 4th bond? Well, it didn't have enough electrons, and electronegativity wasn't so great, but it was great enough to not be stolen from and all this other stuff. But boils down to is it does want an octet. It does want to be like a noble gas and have 4 sets of electrons, 8 total electrons around it. But it brings its 3 to something like a nitrogen group, which would have this lone pair of electrons, right? So this lone pair of electrons here, and they kind of get together. So just because it's not a hydrogen, it's a BF3 that's doing this loitering on the lone pair of electrons. Why can't this still be an acid? Just, that's kind of atomist. So the idea here is that just because it's not hydrogen that's mooching off of you doesn't mean it's not an acid. Anything that has the desire to hover around your lone pair, right? So this guy's hovering in this guy's house, and he's like, "What's for dinner?" And he's like, "Get out of my house." And that's a good sentiment. Just like BF3 is like, "Hey, look, lone pair, let me go play with it." And it hangs out right on top of nitrogen. Nitrogen's like, "Go away." And BF3 is like, "No, I don't want to go away. You have a lone pair here." All right. So that's one thing. So we call this a Lewis acid because even though it has nothing to do with hydrogen, it will hover over electrons just like hydrogen plus would. And we still call this a Lewis base because it's still giving the lone pair up like Bronsted acid would. Only in Bronsted acid's case, we said it was a hydrogen acceptor, but this is not just hydrogen. It's anything that gives up a lone pair. All right, and then the last thing you needed to know was that a carboxyl group in amino acids has an acidic H plus that can come off, and the amino group has that lone pair, so that is basic. And so when you have amino acids, they actually exist with the H plus, and I probably should be doing this in red. The H plus from your carboxyl group actually goes over to that basic lone pair and sticks on there. So this is a basic group and this is an acidic group when you deal with amino acids. And that's just good for you to know if you move on to biology. And that is all I have to say. It's been a pleasure doing these things. I wish you all the best.